Good day, students. How are you all? Now, in our previous lecture, we studied about equipotential surface and electric potential, right? So, let's have a quick recap of what we studied in the previous lecture. Equipotential surface are those surfaces at which the electric potential remains same throughout the surface, right? Like this. At all these points, the potentials are same. So therefore, they are known as equipotential surfaces. Right? Now, again, let's suppose if we have a three-dimensional sphere, right? So at the circumference or on the surface of this sphere, all points are at same potential if there is a charge at the center, right? So this surface is an equipotential surface, correct? Now what's the mathematical expression of electric potential? That is V is equal to Q upon 4 pi epsilon naught d, where d is the distance. So as we have discussed that for electric field and electric potential, for both these two quantities we are supposed to have some charge, right? So basically electric potential can be measured at a particular point due to the influence of some charge, right? So let's suppose this is the charge and d is the distance between the charge and the point. So at point P, the value of electric potential can be calculated by the formula, by the expression V is equal to Q upon 4 pi epsilon naught d, right? Correct. Now let's solve some problem. Now here there is a problem in which it has been given that this is the the figure, this is the diagram. Charges plus q and minus q, they are placed at point A and B respectively, which are at 2l distance apart, right? Means the distance from A to B has been given as 2l. Okay, now C is the midpoint between A and B, means C is the midpoint, so AC must be equal to CB, and that is L. So therefore the distance from A to B is 2l, right? It has been given in the problem. Next, what is the work done in moving charge plus Q along the semicircle CRD? Means we have to move a charge plus Q along the semicircle CRD, which has been given in the problem. So we need to find out the work done, right? So to find out the work done, what is the definition of work done is basically the potential difference between this point and this point. If we multiply with that charge, we will get the work done in moving the same charge from this point to this point, right? This is the concept. Are you getting? So basically the concept is that when we have to find out the potential difference between 2 points, so we need to bring a unit charge, right? We need to bring the unit charge and then we need to move it from this point to this point. So the work done will be that potential difference. But here we need to find out the work done. So we need to multiply the charge which we have to move from this point to this point to the difference in potential between these 2 points. Correct? So what will we do in this particular problem? We will find out the potential, the net electric potential at point C, and then the net electric potential at point D, and then we will take the difference and then we will multiply it with this particular charge plus Q, which has to be taken from this point to this point through semicircle CRD, and that will be our answer, right? So we need to apply the formula that we have studied here. The electric potential at point P can be calculated by the formula V is equal to Q upon 4 pi epsilon naught D. Okay. Now let's have a look here. In this particular problem, this distance is L, this distance is L, and this must be L because this is a semicircle, right? Here the point charge plus Q has been placed, and here at B minus Q has been placed. So if we look at here, so this particular point C is equidistant from plus q and minus q, and both are having opposite sign. Okay, so what will happen? They will nullify. So here we will not get any potential. The potential at this particular point, net potential at this particular point will be 0 due to both these opposite charges. Correct? Now we need to find out the potential at this particular point D. Are you getting that? Now at D, if you see here, the plus q charge is here the minus q charge is here. Now minus q charge is closer to this particular point D, whereas this plus q charge is far from this particular point D, right? So what will happen? This minus q charge will dominate here in finding out the effective electric potential at this particular point, right? However, this will provide the positive potential and this minus q will provide the negative potential here, right? So how will we calculate? Just pay attention. Now as we have already discussed that at point C there will be 0 potential, so Vc will be 0. Now we need to find out the effective, the net electric potential at point D. So that will be, again we need to apply the formula 1 upon 4 pi epsilon naught, then the electric potential contributed by plus q charge and minus q charge, right? Now look at here, this is q, so q divided by 3l, because this is l, 1l, this is 2l and this is 3l. So this distance of the charge to the point is 3l, so we have divided it with 3l, right? Now here there is a negative charge is here, so minus q, again 1 upon 4 pi epsilon naught, therefore it has been taken common in both the terms, divided by q by L, right? So q by L, L, this is the distance B to D. Okay, so here we have written here. So the final value that we are getting, the final value of net electric potential at point D is minus q upon 6 pi epsilon naught L. Okay, now we need to find out the work done in moving a charge plus q from this point C to this point D. Okay, so this work done can be calculated by multiplying that charge with the effective potential difference between this point C and D. Okay, so now as we know that Vc is 0 and Vd is negative, so potential difference Vd minus Vc will be, multiply this charge q with this, we will get the final answer. So it's okay for today. We will continue solving more problems and concepts in the next lecture. Thanks a lot.